So something to pay attention to in this question is the fact that an angle is given, and the problem really talks about distances along the length of this incline, but everything to do with energy is all about vertical distances, vertical positions. And so we'll have to be using some trigonometry to make some connections there. So first of all, part A asks how far along the ramp will the mass travel, assuming it does not fall. So the fact that it's asking how far will it travel is pointing us to the fact that it reaches its maximum height. And when it reaches that maximum height, the speed will be zero, the kinetic energy would be zero. So what we basically have here in part A is that the energy at the bottom, or maybe you might just call it E1, is going to equal the energy at the top. And at the bottom, we're at the lowest point, so we'll set the potential energy equal to zero, and that means we only have kinetic energy. And then at the top, because we're coming to a spot where the object stops for a moment, there's only the potential energy. But in terms of the potential energy, we're looking for a distance d, not the y that we normally are using here. So we could either find a value and then kind of work our trig, or we could work our trig now. So I'm going to go ahead and make the substitution that because y over d is equal to the sine of my angle, that d times the sine of 40 would give me y. So let's put in a few values. Notice that our masses cancel out again. So 1/2 times our initial speed of 4.6, make sure we square, is going to equal 10 times, and it's not going to be, it'll be 10 times y, and again, I could find y first, or I could substitute d times the sine of 40 and solve for d instead. And if I do that, we end up with d being 1.65. All right, the second part of the question says, well, you know, that's how long the ramp would have to be. But what if we had a shorter ramp? What if the ramp was only 1 meter long, meaning that it would stop, you know, probably somewhere around here. And so the question then is, what's the speed of my mass when it gets to that point? It would still be moving upward on the incline. And so in that case, our energy thoughts change. So we'll say that our same E1 is now equal to a different position, which we'll call E3. We still would have the same initial energy for the system, but now I have a second kinetic energy to deal with. When I reach this spot I've marked in red, there is kinetic energy here. I know that because it wants me to find a speed, so obviously it would have to be moving. So I'll just distinguish between those speeds by calling them V1 and V3. And then it's above the ground again, and so that would be m times g times y. But again, they're not giving me y, they're not giving me that distance, they're giving me a distance along the incline. So I'm going to go ahead and make that same substitution, d times the sine of my angle. And I can again cancel out my masses, which is nice. I probably would have messed up my conversion or something. And so we have 1/2 times our 4.6 squared, that initial speed coming from the push. And then I don't know the speed of the mass. I'm just going to lose my subscript here since I've kept everything organized at this point. And then 10 for g, 1 for my value of d. I'm not going to drop that out in my head. I'm going to make sure I mark it down so everybody understands what I'm doing. And then the sine of 40. And so as I go through my algebra and so forth, this should come out to be about 2.9 meters per second.